Hello. I'd like to talk about the KLT algorithm today. It stands for Kanade-Lucas-Tomasi algorithm. It's a checking algorithm, and it's basically introduced by Kanade in the early 80s with his two students, Lucas and Tomasi. It's actually a series of papers. The first one is by Lucas and Kanade, so therefore sometimes you see an LK algorithm, something like that, or LK checkers. Basically, maybe I will just first give an example here. This I got it online. Okay, it is I need to probably close it and run this again. So this example is just, you see, like it's checking like this couple vehicles. It's doing quite a nice job. I'm also checking some other things. Sometimes it loses the check, but most of the time it's working okay. So let's look at how it's done. So there are lots of variation, but for the most basic form is like this. We have these 5 steps. First, we'll just detect Harris corner, basically some Harris corner detection. Just detect some corners in the first frame. And for the next step, we will try to compute motion for each Harris corner between executive frames. So this motion can be translation, affine, or many different variations, as we will see later on. In the third step, we will then link the motion vectors in successive frame. In such a way, we'll get a check of each of the Harris points. And then we'll introduce new Harris points every once in a while, let's say every 10 or 15 frames. Eventually, we'll just go back and create new Harris corner points and redo the step 1, 2, 3. So as you can see, actually, the trickiest step is basically the step 2. And this was kind of addressed by the first Kanade's paper, basically Lucas-Kanade original paper, and typically it's called the Lucas-Kanade checker. And that's what we'll focus here. So the key step of the Lucas-Kanade algorithm is to find the mapping of a patch in the current frame to another patch in the next frame. So it's really just a registration problem. And there's lots of flexibility of what choice of motion we can pick, or like what choice of registration we can pick here. So we can have translation, simple translation transform. So it's just shifting the coordinates. Or we can have Euclidean transform that is basically a rotation and then shifting. We can have similarity transform that's basically rotation, then translation, followed by scaling. And we can have affine transform and also projective transform with increasing capacity. So here's some of the equations for this transformation. So let's say we have translation is basically just shifting the coordinates. So we start with coordinate xy and shifted by b1 and b2. And then we have rigid transform that this part is basically the rotation, then followed by shifting. We can have affine transform. Then in this case, all these coefficients are basically independent, so it's even more flexible than rigid transform. And also we can have projective transform like this, but you see that like this is no longer linear, and also it's actually not even polynomial. So for that matter, sometimes it's hard to manipulate. Therefore, we have some approximate transform that typically used to approximate this projective transform. So for example, we have this polyquadratic, bilinear, and pseudo-perspective transform. Okay, to continue our discussion, we need to review some of the calculus. So let's first look at Taylor series expansion, and in this case, more precisely, the first order expansion. So let's say if I have a scalar function fx, and I would like to expand fx lot plus delta x, so it can be approximated by fx lot plus the derivative of f at x lot multiplied by delta x. So we have a figure something like that. If this is a x lot, if this is delta x here, then at this level here is fx lot, right? And this level is fx lot plus delta x. So therefore, like this difference here is approximately f df dx at x lot multiplied by delta x. So it's just simple calculus. And so if you consider now a little bit more complicated case, that f is now a vector function. So I have a big F here is composed of f1x, f2x, and so on up to fmx. And its argument is also a vector, so it's like x here, where the x is x1 up to xn. Then I can expand again like f1 x lot plus delta x as f1 x lot, but because like f1 now is a function of a vector like x1 up to xn, so I need to add up all the influence. So it's like it will be like basically each of these terms like partial derivative f1 with respect to x1 multiplied by delta x1 plus partial derivative f1 with x2 multiplied by x2 and so on up to xn. So I can do the same thing for like f2x and up to fmx. So I have basically here is m equations, and know that here this part here I can actually represent this by a kind of vector dot product. So basically this part is really partial derivative. It's not writing. So oops. Partial derivative of f1 x1, f2 x2, and so on up to f1 xn multiplied by delta x1, delta x2 up to delta xn. And I will denote this vector here as just delta x here. So therefore, the first equation will eventually represented by just this part here, this multiplied by this, and it's like this is basically a vector f1 x naught, and the m equations here will be nicely represented by this single vector equation. And this matrix here, we'll call it a Jacobian. It's essentially just a generalization of derivative to vector functions. Okay, now we can continue our discussion for finding the optimal warping or the transform. So our transform, as we mentioned earlier, can take lots of different possibilities. Let's say we can just have like translation or literal transform or perspective transform or any other transform basically. And all this transform will be parameterized by some parameter. Let's say we will denote it by P. This is a vector parameter. So what we want is like the image, the original image. After it warp it, so let's say consider original pixel x. Now it warp it to, so it map to some other pixel like wxp, and this warping of course will be parameterized again by this p here, and we hopefully after warping this image it will map very closely to the template image that our target. And so we want to make sure that like for each pixel it will be similar. So we need to sum over all the pixels. So sum over x, and we'll just take the square difference here. Okay, now, so essentially, basically, we're just trying to minimize this function with respect to p here. So this is actually just a scalar function. So the optimum approach is the typical approach is just taking the gradient of that gradient p. The ingenious idea here is that instead of doing that, take the gradient of p directly because it's hard to tackle. What we're trying to do is we're just trying to substitute p by p naught plus delta p, and instead we think of p naught as just something fixed constant p here, and we're just trying to optimize in terms of delta p, and delta p is supposed to be small, so therefore we can do Taylor series expansion for that. So therefore, instead of trying to minimizing this guy, we're trying to minimize this, and to do that, we will take the derivative of this guy with respect to delta p and set it to 0. And if delta p is small, then we can try to expand this with Taylor series expansion that we already described earlier. And note that I want to emphasize that x is treated as a constant here, so only p are the parameters. So I will try to expand IWP plus delta p around p naught here. So therefore I first have this term here, and then this term here, and then I will have basically the Jacobian of this function with respect to delta p. In this case, actually the gradient because it's a scalar function. And this gradient is essentially because this is a composite function, so I need to first take the gradient of I multiplied by the Jacobian of w with respect to p, and then multiplied by the difference delta p here. So far so good. So now therefore instead of considering this guy here, so we'll consider this guy, and what we're going to do is take partial derivative of this guy with respect to delta p and try to set it to 0. So if we solve it, we get delta p is equal to 0, then we are done. Otherwise, we can use that delta p to modify the current p naught. So therefore, it's really an iterative algorithm. We keep using this equation, find delta p, and then adjust p, and then do it again and again. So now, first we need to find the derivative of this guy with respect with delta p. So, okay, it looks complicated, but it's really pretty simple because this is really just a scalar function, and you can think of this whole guy as, let's say, fx here to the square of fp squared to square, and then so therefore it's really equal to, if I take derivative with respect to p, I will have 2fp times gradient of f, right? So therefore I have this this guy multiplied by this essentially the fp here, and the gradient of this guy, the first term does not depend on delta p, so it's 0. This does not depend on delta p, and this guy is essentially just like some constant times delta p here. So therefore, I take the derivative with respect to delta p is just equal to this constant a here. So I have this here. So then afterward, I can just pull the terms that do not have depends on delta p on one side. That basically these terms multiplied by this guy, I put it here. So on the other side, I have a negative sign, and also I have tx multiplied by this guy. I have this negative sign become positive. Therefore, I have this here. So I ignore this 2 because it's okay. I can just take 2 equal to, remove that constant here. And so now for the delta p, it's just this term multiplied by this term and this here. So therefore it's pretty nice. I have all terms on one side of this multiplied by delta p equal to these other terms here. So, and note that this is actually a matrix. So I just take inverse matrix of this thing on both sides. Then I have this here, and then this matrix we call H is equal to this guy here. So then we find out to be essentially. So that's basically the whole algorithm. So we will just start with some p, some arbitrary p, then trying to compute delta p by this equation, and then we updated p by p plus delta p, and then substituting the equation to find the new delta p again and again. So let me summarize the, okay, before I doing that, let's just give an example. So let's say if as I mentioned, like this warping function can take many forms, and if I just consider translation, then wxp can be just represented by x plus p. So if I want to find the Jacobian, then it will be something like take delta x partial derivative of x1 plus p1 with respect to p1, and then partial derivative x1 plus p1 with respect to p2, and so on and so forth. Note that this off-diagonal term here is 0, so this x1 plus p1 does not depend on p2, and x2 plus p2 does not depend on p1, so it's gone. And for this guy here, this derivative with p1 is just equal to 1. So I have a very nicely just hat is equal to an identity matrix. And then like recall that we actually need this term here, delta I multiplied w delta p. So and for that is simply equal to just del I del x and del I del y. And therefore the Hessian matrix, the H is just equal to this, okay, this I take the chance will become delta I del x, del I del y, and then if I this multiplied by this guy is just equal to this here. And by the way, this guy, this H here is really just a Harris corner detector. This is what we just compute is the Jacobian del W del P for the translation transform. So we can essentially do the same thing and compute the Jacobian for different transform, and for example for rigid transform will be equal to that, similarity transform that, and so on. Leave you guys and basically you can just it's a very simple exercise if you want to try it. And so now we can really summarize the algorithm. So essentially the whole Lucas-Kanade algorithm is summarized by this equation that we derived earlier. So we start with some image and with some template diagram image. And what we're going to do, we will start with some arbitrary p as the warping parameter. And then we try to warp I with wxp. Afterward, then we subtract I from t. I got this guy here. Then compute gradient of I is equal to this guy. Then I compute Jacobian so that w del p at x and p. And then I compute the steeper descent that basically this guy here, del I del w del p. And then I compute the Hessian is H is given by so this multiply this multiplied by this and sum over x, and then eventually I can compute the error is this thing here. So it's like I compute this guy, basically this whole term. So then compute the del p, so just got this whole thing here. Then I update parameter p. So I just repeat this whole process again and again. Okay, now let's look at some variation of the Lucas-Kanade algorithm. Basically, those variation is trying to address one issue that the Hessian matrix here is quite computationally intensive to compute. So what we want to do is that we'll try to avoid computing this repeatedly. So what precisely what we're going to do is like in the previous step, we need to solve this equation, trying to find the partial derivative of this expression and set it to 0. Now, what we did is that we warped the image with parameter p0 plus delta p, but instead, like we can really warp the image twice. So we can warp the image first with p0 and then warp again with delta p. And if we continue to derive just like what we did previously, we will get an algorithm known as a compositional algorithm. But this is not our end goal, basically. Our end goal is to derive another algorithm is even nicer. So more interestingly, we'll just modify this equation a little bit. So because this delta p is essentially just a dummy variable, we'll consider minus delta p instead. So actually it doesn't matter if this is just keep consistent with the paper. Otherwise we'll just again continue to derive the equation without any problem. But now the key point here is instead of warping the image twice, first by p0 and then by minus delta p, instead in the second warping, we don't really need to warp the image by minus delta p. We may warp the template or the target image by delta p instead. So think of like you have this image here, you warp by delta p or like minus delta p such that it's matched with this guy here. But instead, we can also like warp this guy by minus delta p to get into this space and try to match these two. So if we do that, so we have this equation instead. And this is actually a very interesting equation, as you will see. So if we continue to derive this, again we have a delta p here, we can do a Taylor series expansion, assuming that delta p is kind of small. And then because delta p, we can really consider it as 0 plus delta p, so we can expand this as twx0 plus the derivative or like the Laplacian, the Jacobian of this tw with respect to p multiplied by del p. And the Jacobian of that is just the gradient of t multiplied by the Jacobian of w with respect to p. So then if we take the partial derivative of this whole term here with respect to delta p, then again I will have something like this, 2 times this expression, and then take the derivative of this guy, these two with respect to delta p, these two will be 0, and we only have this term left here. And note that like for this guy here, if we warp the template image by parameter 0, it's essentially not warping it. So therefore we just have tx here. So then we can rearrange the term like last time to find delta p, and we will get this. And it's a very similar equation, but note that now this time the Hessian, this h here, is really equal to this guy. It's equal to the partial derivative, the gradient of t multiplied by the Jacobian of w with respect to p. But note that this time it's computed at 0 instead of at p0. And p0 in the previous case, for each iteration, it will change. So, but in this case, it doesn't change. Therefore, like we only need to compute this Hessian once. So now we really have this equation. I copy here, like back in here, and unlike last time, we can look at like each step that is needed to compute this delta p. So what we're going to do is first we'll warp the image by parameter p, that p can initially be kind of arbitrary, and then afterward we'll subtract t from I, And then I will compute the gradient of t. This, by the way, we only need to compute it once. And then we can compute the Jacobian partial w partial p at the point at the point of p equal to 0. So therefore only need to compute once also. And then we compute this gradient t multiplied by partial w partial p. Again, only need to compute once. And then we compute the Hessian again, it's only once. And then we can compute this whole term here. And then we can compute this delta p as this term multiplied by h inverse. And then we can update p and then repeat the whole things again. But note that these steps from 3 to 6 essentially not change. So therefore we can really pull it out. So we'll have something like first initialize that we compute the gradient of t and then compute the Jacobian partial w partial p at 0 p equal to 0, and then compute the steeper descent, that's gradient t multiplied by partial w partial p, and then compute the Hessian. And then in the loop, we'll just compute the remaining step. Basically, warp the image by p, and then subtract t from I, and then compute this expression here. Note that this here is fixed, so we don't need to recompute it. Then we compute delta p is equal to this guy multiplied by the inverse Hessian. Again, the Hessian does not change. So, and then we update p, and just repeat this, just look for these steps here. And so this is a basic figure that I extracted from the original paper by Baker that actually first described this algorithm. It's a pretty nice paper with a title, something like 20 years of Lucas-Kanade algorithm, something like that. So as the name suggested, it's really at the time it's the 20th years of the introduction of the algorithm, and it kind of introduced this nice modification that speed up the algorithm quite a bit. I won't go into detail of this figure because it's essentially just repeating what I talked about in the previous slides. So I guess that's all for me, and I hope you find this useful.